Hello everyone, I hope you guys are doing great. In this video, I'm going to quickly show this model that I created that uses couplings everywhere. And this is related to this blog post from my blog Learn FEA. This blog is related to Abaqus Surface-Based Coupling Constraint. The main video of this blog post is this one where I show how to create a coupling for a simple model in Abaqus using Abaqus interface. And at the end of this blog post, I have here a case study that is a ball joint connection. And this is the model. I'm not going to teach how to create this model from scratch here in this video. I'm just going to show the model details. And if you're interested in learning how to create this model from scratch, please leave a reply at the end of this blog post. I'm going to let the link to this blog post in the video description, or you can comment on my video on YouTube. Okay, so this video is going to be posted on YouTube. Okay, now, so this type of connection, ball joint connection, is found in many types of connection between structural components. And one good example is on the front suspension of vehicles. So on the front suspension of vehicles, we have, for example, between the knuckle, that is this part, and the upper control arm, that is this part, we have a ball joint connection. And you see that we have here the ball stud, and then we have a housing, and we have the nut here, and then we have the upper control arm and the knuckle, and the housing is in the knuckle. Okay, this is also found here between the lower control arm and the knuckle, and also between the stab bar and drop link and etc. All right, so this is the model I created. I created this model using ANSA. ANSA is a preprocessor software. You can search for ANSA Meta. Sorry, this is Meta. ANSA preprocessor. So ANSA is a preprocessing software that can be used to build a model that's going to be solved in Abaqus, for example. It can be used to create models to be solved in many types of solvers. So we have here Nastran, LS Dyna, ANSYS, Abaqus, everything. So we can use it to build a model to be solved in Abaqus, and then we just need to import this model in Abaqus using the .inp file and solve it. And after solving it, we can use the .odb file in MetaPost. That is another software. This software is for post-processing. So MetaPost is from Beta also. You can search for it, MetaPost. So MetaPost is a post-processor software. That is, we can process the results after it has been solved in Abaqus. Okay, so the whole process is, firstly, we build the model in ANSA, and then in ANSA, here we have my model. In ANSA, I can go to File, Output, Abaqus, and then I'm going to output a .inp file, and then this .inp file can be imported in Abaqus and solved, and can be solved. I don't need to do anything in Abaqus. I just need to solve the model, and then after solving it, let me show you what is the results. I will have a file with extension .odb, and this file can be opened in a post-processor software such as this one. And here we can extract contour plots of stress, strain, displacement, and etc. Okay, so let me show the details now about this model in ANSA, where I created the model. Okay, so this is kind of simplified. Here I wanted to this looks like a stabilizer bar, a connection between a stabilizer bar and drop link. So imagine that this part right here is a part of the stabilizer bar. It's just the end of the stabilizer bar. It's not representing the whole part. This is this one here is the ball stud, and then we have a nut here. Notice the shape of this ball stud, how this is. Okay, so we have this surface here. Let me show it. We have this surface here. Let me highlight it. This surface here that will be in contact with this surface when we apply bolt pretension for this ball stud. We have this nut that will, and then we will have a pressure between this surface and this surface when we apply bolt pretension. Okay, and also we have this green part that is representing here, in this case, the drop link. Let me see if I can find an image of this stabilizer bar. Let me see if we can find an image that shows this type of connect. Okay, so this image is pretty good. So you see that, let me get copy. Let me get open board. Okay, so you see that you have here the stabilizer bar is this bar. And then this is the end of the stabilizer bar. That is this part here that I have modeled. So I have just modeled the end and I simplified the geometry. So we have like something like this. And then we have here the ball joint. And this is the drop link. So this is the drop link, which is this part that has the housing for the ball stud. Okay, so this is the drop link. And this is the ball joint. We have a nut here, a thread, and then the ball stud is here inside. Okay, so this is what I have modeled as an example in ANSYS. Okay, now that you understood what are each part, let me also get here an image showing a ball joint. Okay, so you see that in a ball joint connection, this image is good. We have one part. Let me get an image here also and paste it here on open board. I guess I have closed it. Open board. Okay, so you see that in a ball joint connection, we also have the ball stud, that is this part, and then it has a thread because we usually apply a bolt pretension, so we will have a nut here, and then we will have the other part that is being connected here, just like in our example. And then you see that the ball stud has this spherical shape here, and then we have another part that needs to have a housing that goes around the ball stud. And notice that one very important thing here is that between the ball stud sphere and the housing, there is a material, hyperelastic material. Okay, this is what we have usually. At least for front suspension of vehicles, we have a hyperelastic material that has a stiffness. Okay, this material is not usually modeled because it would make the model too complex. So instead of modeling this material, we use couplings and a connector to connect the housing to the ball stud. Okay, so this is what I have done here in this model, and this is what is done. This is how it's done in reality in companies like in the automotive industry. I work with front suspension of heavy vehicles, and this is how we create ball joint connections in our models. Okay. All right. Now let's start talking about the couplings that we have in this model. So firstly, let me go to constraints here. Constraints. Firstly, we have this coupling. So you see that this coupling is just, so in my blog post, I have here the applications of couplings, applications of surface-based coupling constraint. And one of these applications is for modeling and conditions. So that's what I'm doing here. So since I'm not representing the whole stabilizer bar, here where I have cutted it, I put a coupling, and then you see that we have the reference node here where I can apply loads and boundary conditions. And this reference node is attached to the nodes that are part of this surface. Okay, if I go to this coupling, you see that we have here a kinematic coupling. That is, we will have a rigid connection between the reference node and the coupling nodes. So it will move as a rigid body. You see that all degrees of freedom are constrained, even though the solid elements has just the translational degrees of freedom. So it would not make any difference if I don't consider the rotational degrees of freedom. That is 4, 5, and 6. 4, 5, and 6. All right. Let me see. So this is a node-based coupling. I explain what is the meaning of that here. Node-based surface and element-based surface. To be honest, it doesn't make it much of a difference. We have the influence radius, orientation, everything. Okay, so this is a kinematic coupling for modeling and conditions. We also have the same thing here, a kinematic coupling to model to fix the displacement, for example, at this end and prevent rigid body motion. Also, we have two couplings here that will help me to model bolt pretension. So we have one coupling attached to the bolt end, and one coupling, that is this one, let me show, there's just this one, that is attached to the nut. And then we have a, let me go to connector, we have a translator connector here, and then I apply a connector load to this translator connector to model the bolt pretension. And I have a blog post that explains with details how to model bolt pretension using this technique. You can find this blog post here in this link. Where is it? It's right here. It's this example. So if you want to see it, you can click on this link, and then I have a blog post that explains about bolt pretension techniques. And one of these techniques is just like this. So these two couplings are kinematic couplings. And then we have the translator connector connecting the reference nodes of these two couplings. All right, so we also have the couplings that will be used to connect the bolt stud to the housing. Okay, so let's see. Let me get just the bolt stud. So here we have the bolt stud, and then here we have a coupling, and the nodes attached to this coupling are the nodes on this surface here, on this sphere of the bolt stud. And let me get here the constraints. This coupling, you see that the reference node is on the COG that is automatically calculated by the software. So it's on the COG, so it's inside the bolstered. And okay, so that's one coupling, and in this case, I have created a distributing coupling. That is, I want the load to be distributed between these nodes that are selected on this outer surface. I don't want it to be rigid. And also, if we get this part, we also have a coupling, and the nodes related to this coupling are inside, are in the surface. Let me highlight the surface for clarification. We have this surface here, and every node that is part of this surface is attached to this coupling. And then the reference node is right in the middle. Okay, on the COG that is automatically calculated. Okay, so I have one coupling for this. I have one coupling for this part, and I have and I have another coupling for this part. Now I need to connect these two parts. And how do I do that? I can connect the reference nodes of each coupling. And that's what I have done. So you see that I have this connector right here. And here I have the reference node of one coupling and the reference node of the other coupling. And there is a connector, a joint connector, you see, joint connector between these two nodes. A joint connector simply constrains the translational degrees of freedom of these two nodes. So the translational degrees of freedom of these two nodes will be forced to be equal. But the rotational degrees of freedom will be free. In that way, you see that, let me animate it, you see that the bolster is able to rotate with respect to its housing. You see that it's rotating, right? Because we have just the translational degrees of freedom constraint. Because we are using a join, a translator of the type join. Okay, so this is how we connect these two parts. And in this module, just to end this explanation, in this module, I have simply, let me show the steps, step manager. You see that I have a first step for bolt pretension application. And in this step, I have just applied the bolt pretension. Let me show it. So, okay, so the first step is just for bolt pretension. So look, you see that the bolt is entering the nut. Okay, so this is bolt pretension until here. Until here, we have bolt pretension at the end of step 1. And then in the second step, I have applied here a displacement at this reference node. Let me try to get it here. Okay, yeah, I have applied a 2 millimeter, as you can see here, displacement in this direction. So let's see. At this node, I have applied a displacement to the right, to the left here, actually. Let's see. So you see that this is displacing. I have amplified the deformation here so we can see the deformation better by 10 times. So that's why it's displacing. In this case, it's displacing 20 millimeters. Okay. And while I have applied this displacement, I have fixed all degrees of freedom of this reference node. So that's why we are not having a rigid body motion. So let's see. Okay, I don't have any. Let me see a good way to view it. So you see that while we are displacing it, this surface remains in place because we have a kinematic coupling here attached to this reference node, and then we are fixing all degrees of freedom of this node. So this is kept in place as a rigid body. Okay. And while I apply a displacement to the left here, we have a contact between the ball stud and the drop link. Let me show you. Let me show you. This is the last thing I need to show. Contact. And you see that we have a frictional contact between the nut and the drop link, as you can see here, with a coefficient of friction equals 0.2, which is a pretty standard value that we use for friction between two metals with no surface treatment. And we also have a contact between the ball stud and the drop link. So in the first step, we apply the bolt pretension. And then when we do that, we will have a normal force between these surfaces, and that multiplied by the coefficient of friction yields to the maximum tangential force that we can have in this contact. And then when we apply a displacement here to the left and cause this movement, the frictional force is keeping the ball stud in place. Okay, so this is how this model works. Okay, now if you are interested in knowing how to create this model in ANSA, please leave a comment on my YouTube video or on my blog post. And if many people ask me to do that, I will do a series of videos to show it, because it's not going to be so fast to show it. Because when I create a video like that, I like to explain every detail. And if I'm going to explain every detail, then it's going to take a long time, like, I don't know, maybe 3 hours to explain everything here, even though this is kind of a simpler model. Okay, we have more details here that I haven't talked about, like such as these springs for stabilization and some other stuff related to these step controls. But if you want to know more about it, please let me know. Okay. All right. I hope you guys liked it, and see you in the next video.